We're going to learn how to write chemical equations for ionic substances in chemical reactions. The reason why that we want to write chemical reactions in a slightly different way for ionic substances is because ionic substances, when dissolved in a solution, actually dissociate into ions, and so they're not actually in the form of a molecular compound like covalent compounds are. And so based on what ions are present in a chemical reaction, we can determine what the driving force for a chemical reaction would be by determining what ions come together to produce products. In order to be able to do this, we need to add an additional piece of information to our chemical reactions. And this piece of extra information is the phase of each substance. In most chemical reactions that you see, there will be a subscripted and italicized letter that is written behind that substance. For instance, behind CaCl2, there is an AQ that is written behind that substance. What the AQ stands for is aqueous. And aqueous means that that substance is not in solid form, but yet is dissolved in water at that moment. And it turns out in this particular chemical reaction, there are three substances, the AgNO3 and the CaNO3 are all dissolved in water, and they're reacted together, at least the first two reactants are reacted together to produce, theoretically, the products of calcium nitrate and silver chloride. But it turns out silver chloride is a solid. Okay, so with writing this substance or this chemical reaction in a way that determines what the driving force of this chemical reaction would be, is let's look at each element in its ionic form while it's dissolved in an equation, or dissolved in water. So let's look at calcium chloride first. So calcium chloride, when it is dissolved in water, so it's in aqueous form, actually dissociates in water, and that means that the cation and anions that make up that substance separate. The cation would be calcium 2+, and we know it's a 2+ charge based on the fact that it's in a group 2 element, and then it will dissociate also and produce the anion chlorine minus. Now there is no such thing as a chlorine 2-. It's just that there are 2 chlorine minuses in the substance. And so we take this subscript in that formula and move that to a coefficient to tell us for every calcium ion, there are 2 chlorine ions present. And so let's do this for every substance that is written in aqueous form. So we're going to have the 2 silver nitrates. They're going to dissociate, and it turns out that you'll have a silver ion and a nitrate ion. So this one, keep in mind, is a polyatomic ion right here. So we'll have silver, and silver has a plus charge, but see, this coefficient says that we should have 2 total. So we'll put a 2 in front of that. And then you're going to have your nitrate ion, NO3-, and again, this 2 in front of the whole substance should say that there are 2 of those ions. And let's try this also for our last one, and this is calcium nitrate, CaNO3. And when this breaks apart, and I should make sure that we keep in mind that these are aqueous, as calcium nitrate breaks apart, it will produce a calcium ion, and it's only one of those, but it turns out it will be 2 anions of nitrate, NO3- with a 2. It is very important, and you cannot forget the charges on their respective ions. They're required to be there. Okay, so now what you're going to do is I want you to write the equation that we have up here. I want you to write this entire equation, but now let's replace all of the substances that are in aqueous form in phase with their respective broken apart or dissociated ionic forms. So basically we're going to take these guys and replace them in the reaction that we have written about. And so when we do this, it will look something kind of like this. So I'm going to move this up just a little bit. We'll start with our calcium chloride. We'll have Ca2 plus 2 chlorine minuses. Now, things start to get pretty crazy and look very busy. So a lot of times what we'll do is we'll bracket around the two ions for that particular original calcium chloride up here. So we'll just bracket it. And so now we're going to put our plus sign, and now we're going to do our second substance, silver nitrate. And so we're going to put a bracket and put our 2 silver pluses and our 2 nitrates. And then we're going to put our yield sign. And then we're now going to do our third substance, calcium nitrate. So we're going to bracket calcium 2 plus 2 nitrates and into the bracket. And you're probably wondering, well, why did I not break apart calcium chloride like I did the rest of the substances? Again, keep in mind that you can only do that with substances that have AQ written as their phase in the chemical reaction. So AQ is the only option. If you have solids, liquids, or gases present as the phase, so this one would have a solid, you cannot break that particular substance apart, and it must reside in the new written form just as it is in the original. So that means we're going to have a 2 AgCl here, and we'll just go ahead and make sure that that solid symbol is there. So this is a new way to write a chemical reaction with all ionic compounds. These are the ones that dissociate in water, written in ionic form. We call this particular reaction something, and the term we use is complete ionic equations. But see, this doesn't really tell us what the ultimate goal of the reaction was. Is like, how do we produce our products, especially if ions are just floating around in water. So it turns out that once we have written the complete ionic equation, we can pull things out of the equation that really did not contribute to the reaction at all. And we call these particular things spectator ions. And spectator ions are essentially an ion which doesn't contribute to a chemical reaction. Well, how do you know if a ion is a spectator ion? Well, it's very easy. You look and just see, is it the same written ionic form on the left side of the chemical reaction as it is on the right side? And so it looks like here at calcium 2 plus. Is there an actual calcium 2 plus written exactly like that on the right hand side? And it turns out there is. Since they are written exactly the same, we consider those spectator ions, and we can pull those from the chemical reaction, and we can just go and cut them out. So stop the video right now. I want you to look and see if you can find any other spectator ions in this reaction. And when you come back, we'll find the other one. Okay, so you're back. Let's find the other spectator ion. Did anybody figure it out? It ends up being nitrate. So NO3 minus, there's 2 of them on the left, and it turns out there are 2 of them on the right. Keep in mind, this whole time we're having a balanced equation too. We're still keeping everything balanced. They're the same on the left and the right, so we cut those out. That's the second spectator ion. It doesn't look like there are any more spectator ions, so because you might have chlorine over on the left, but see, it's written as an ionic form on the left, but not an ionic form on the right, so you cannot pull those as a spectator. So we're kind of done finding spectator ions. What we'll do is we'll just write whatever's left over. And you don't need to continue to keep brackets in that. We'll just write every single thing that's left in the reaction. So we'll have 2 chlorine minuses and 2 silver pluses, and then we have our yield sign, and then we're left over with 2 silver chloride solid substances, and this still balances element symbol wise. And this particular reaction, we have a name for it too, and it's called the net ionic equation. The net ionic equation. So what can we tell from the net ionic equation? We can determine what's called the driving force of the reaction. And for this particular one, it's the formation of solid silver chloride. Okay, so that's how you write a net ionic equation. So what the rest of this video, what we're going to do is just practice several examples. So you can look at, I think I have 2 or 3 more examples. You can watch the rest of those, fast forward through if you need to, or stop as you get the equation and practice it first and then come back and look at your answers. So the first example that we're going to practice is lead to nitrate with reacting with sulfuric acid to produce lead to sulfate, which is solid, and nitric acid. Now, if you'll notice, these 3 substances are written as aqueous solutions, and so we must separate those in order to find the net ionic equation of this reaction in ionic form. And so at this point, what I'm going to do is I'm going to go ahead and just try to write my complete ionic equation as I go and determine each set of ionic components of each of those aqueous solutions as I'm writing that ionic equation. So it turns out for lead to nitrate, the 2 ions that I'm going to have are lead 2 plus and NO3 minus, and I'm going to have 2 of the nitrates, and I'm going to bracket that. And then for H2SO4, sulfuric acid, I'm going to have H plus and SO4 2 minus, and it turns out I'll have 2 H's, and I'm going to bracket that. Yields, and then I don't write anything solid, liquid, or gas in any other form than what they are, so we don't separate them in ions, so I'm going to leave lead 2 sulfate as is, and then I'm going to take my nitric acid and write it in ionic form. So I have H plus and NO3 minus, and keep in mind there's a 2 coefficient here, so I'll put a 2 here and a 2 here and bracket that. So now my next step is to determine my ionic or spectator ions, and the spectator ions in this particular equation are going to be my 2, find our right symbol, my 2 nitrates and my 2 H pluses, and then nothing else is considered a spectator ion. So I will cut those out of my chemical reaction and write what's left over to form my net ionic equation. And that's Pb2 plus SO4 2 minus yields PbSO4. in solid form. So that is my net ionic equation. What's the driving force for this reaction? Well, producing solid lead-2 sulfate. All right, let's try another practice problem. This problem is calcium hydroxide plus hydrobromic acid that would yield calcium bromide and water. And in this particular reaction, if you'll notice, I don't have a solid substance that's created, but I do have a liquid one. And remember, it does not matter if it's solid, liquid, or gas. It doesn't matter which one, as long as it's one of those three. No separating the elements into cation and anion. So again, what we're going to do is our complete ionic equation. And so we're going to take calcium hydroxide first. That means we're going to take a calcium 2 plus and write that with OH minus. That's a hydroxide polyatomic ion. You'll have 2 of those because of the 2 subscript here, bracket. And then we're going to take HBr. We'll separate those into H plus and Br minus. And remember, you have 2 of them from the coefficient in front of the substance, so we'll put a 2 and a 2, and we'll bracket. In calcium bromide, we'll have a Ca2 plus Br minus, and because of this 2 subscript, we'll say that there are 2 bromine or bromide ions, and we'll bracket, and we'll write our H2O, our 2 H2Os, still in molecular form because they're a liquid, not in an aqueous solution. So we'll go through here and determine what our ions, spectator ions happen to be. And it looks like, well, I've got at least Br minuses, 2 of those. And it also looks like I have calcium 2 plus and nothing else there. So I'm just going to write what I have left over to form my net ionic equation, and my net ionic will be 2 OH minus, or 2 hydroxides, plus 2 protons, which are H pluses, to yield 2 H2O. And so that's your driving force of this reaction, is to produce liquid water. All right, so let's try another one. I think this one's going to be a little bit more difficult. In the sense that you have to really follow the rules here. So our chemical equation is calcium cobalt. It reacts with sulfuric acid to produce calcium sulfate, carbon dioxide, and water. And what you want to note here is that the one of our first reaction or reactants and all 3 of our substances as products have the symbol of solid, liquid, gas, right? They've got at least one of those. So it means none of those can break apart into ionic form, but we do happen to have one, this guy right here. So it's not more complicated technically, but it's a matter of just follow the rules. So here we go. So follow the rules. Something that's solid, you just write as is for our complete ionic equation. And so that's calcium carbonate plus, and now we do come to our aqueous, which is, we'll have H plus and SO4 2 minus. It turns out we have 2 H pluses because of the subscript here, and we'll bracket. Yield sign, we write as is, calcium sulfate, which is solid. Write as is, carbon dioxide, which is a gas. And we'll write as is H2O because it's a liquid. So now your job is to look at and determine what is a spectator ion. Well, it turns out that there is no spectator ion in this reaction. So what do? You just write everything that's there as your net. And this is one example of how the net ionic equation and complete ionic equation are the exact same. So for our net, you'll still have calcium carbonate plus, well, and we can leave off the brackets if you want to. We can do 2 H pluses plus SO4, 2 minus, yields calcium sulfate plus carbon dioxide plus water. And you can go and put the phases on each of these. This would still be aqueous, and so on. And so that would be your net ionic equation. And the driving force for this, you would just say, is the formation of solid calcium sulfate, gaseous carbon dioxide, and liquid water. Okay, so those are 3 or 4 examples of how to do chemical reactions that have ionic substances in them and how to write those in net ionic form.